Thank you. All right, thanks for that reminder. Okay, what do we got here for 25 milliliter sample of propanoic acid? It's a weak acid, was titrated with potassium hydroxide. The equivalence point was reached at that concentration. What's the concentration of the propanoate ion at the equivalence point? So the propanoate ion is like the oxalate ion, the acetate ion. So it's the conjugate base of this weak acid, and it's at equivalence point. So we know that it's a 1-to-1 ratio also. So you can figure out the moles of hydroxide that were titrated because you have the concentration, molarity times the volume. That has to equal the moles of the acid. But it's at equivalence point, so none of that's left. And so that number of moles created the conjugate base. So all you need to do is take that number of moles of conjugate base and divide it by the total volume of the solution, and you have its concentration.
Okay. I did an M1V1 equals M2V2.
That's the dilution law.
Okay.
Yeah, what I'm
I gotta
saying.
find moles first. Okay.
Yeah, and then realize that it's at equivalence point. So here at equivalence point, and we'll take a look at this today in our discussion.
Yeah, okay, that's fine then.
For
Yeah.
titrations, but I just want to give you a little foreshadowing since we're on this problem, and that is that equivalence point, the number of moles of acid equals the number of moles of base, which reacted to completion, wiped out each other, and it created that many moles of conjugate base. So all 3 moles equal, but the 2 reactants are gone now, and all you have is the product.
I think I see what I did. I need to find moles and then do it and then convert back into molarity.
Using the total volume. Yep.
Yeah. Okay.
Okay, awesome. All right, any other quick questions? Well, we're going to get into this a little bit more in a few seconds, I think.
I only had a question on 23. That's about it. Just like how exactly would you
go about it? All right, let's see. It says what volume of that sodium hydroxide of that concentration must be added to that volume, that concentration of the weak base to achieve a pH of 8. The Ka for that is HOCl, 3.5 times 10 to the minus 8. So it is a weak acid. So they're telling us that we have to neutralize enough of this weak acid to achieve a pH of 8.00. And they give us the information to calculate moles of the HOCl. And we need to figure out what volume is going to is needed to introduce a certain number of moles of NaOH. So this is kind of like a titration problem. And so you're going to have to know what happens during a titration problem and how the pH changes as the 2 reactants are mixed. And once you study that, that's going to give you a hint as to how to solve this. So again, it's a titration type problem, which we haven't talked about yet.
Okay, thank you.
Yeah,
that definitely helps.
Yeah, so let's keep that in mind when we go through titrations, and that's right where we're at right now in our discussion. All right, then I'm going to get rid of this and let's get to the discussion. And this is where we left off yesterday. We were talking about titrations and titration problems. So just to refresh your memory, in a titration, we have certain categories of titrations that you're going to need to recognize and deal with. So we have the strong acid, strong base titration. You don't need any ice tables for calculating any of the concentrations and therefore pHs that go along with that. It's always a limiting reagent. One is in excess unless it's at equivalence point, at which time there's the same amount in moles of acid, strong acid, reacts with strong base to form salt in the water, and you know the result of that is going to be a pH of 7 because in the salt you have ions that are spectators. That's different from these other cases here. As you titrate in a strong base into a weak acid, or you titrate in a strong acid into a weak base, then we have to look at the kind of like a buffer problem, where the first reaction that takes place is one to completion of a strong with a weak. And if it's before the equivalence point, then we have some of that weak left over. And we need to write up the ice table for that and figure out how much is left over and its new concentration, figure out the concentration of the conjugate that was created at that point in time in the titration, and add that to the ice table. And we'll see how to do these types coming up. All right, so this kind of talks you through it, but I like to get to the pictures. So in these in these titration problems, you are either titrating a strong base into an acid, and that acid could be weak or strong, or you're titrating a strong acid into a base, and the base can be either weak or strong. So this is an example of a titration into an acid. And I recognize from the shape of the curve here that it's probably a weak acid because it starts up higher and it's slopier here in the middle, whereas a strong acid, strong base titration is flatter down at the bottom. And then it goes through a large inflection region for the strong acid, strong base titration. So this is probably a picture of a weak acid that's getting titrated. And I know it's the acid because it starts out acidic, and then I'm adding in the base. So the questions center around 3 different points, and your ice tables are going to be slightly different at those points if you use any. It turns out at this 4th spot, you don't need an ice table. But the first question that's sometimes asked is, what is the pH of the solution before any base is added? So that's just a simple ice table, and we'll see that. And then the second type of titration problem is, what's the pH after a certain amount of base has been added, but it's before the equivalence point? This right here, number 2, is in that region where you're adding some, but it's before the equivalence point. And this is called the buffer region of the titration. Does anybody know why that's called the buffer region?
Because it slows down.
Now, be careful with your words. it doesn't slow down. That's a kinetics thing. When we look at rates of reactions, we talk about speeds. So it's the reaction isn't slowing necessarily. We don't really know too much about the speed, but it's an acid-base neutralization, and usually they're fairly quick. Why do they call this the buffer region? What's slowing down is the change in the pH, right? And the reason is because in this region, you're creating a buffer. You have some leftover weak acid because it's not to the equivalence point, and that part of the weak acid that has reacted, that has been neutralized, created the conjugate base. So now you have a weak acid in the presence of its conjugate base type of equilibrium in this region, and that's why they call it the buffer region. Okay? Now, the third point in these problems is right at the equivalence point. That's when you have an equivalent amount of acid has been reacted with an equivalent amount of base. Now notice that I'm careful and I say equivalent and not equal. It's equal if the reaction between the acid and the base is 1-to-1. Then it's equal number of moles. But what if it's 2-to-1? Then the equivalency is, well, 2-to-1 or 5-to-2 in some cases, or whatever those stoichiometric coefficients say. That's what's known as an equivalent amount, the stoichiometric amount. And that's why it's called the equivalence point, not necessarily equal. A lot of the times it is because the stoichiometric coefficients are 1-to-1. So you have to remember that when you go to figure out these problems. You need the balanced equation, the ice table, and those stoichiometric coefficients. Now, after the equivalence point, you remember all those curves kind of melded into the same. And the reason is because after the equivalence point, the pH is dictated by the excess strong base. You don't have to worry about the conjugate base anymore because the amount of hydroxide generated from the weak base is negligible compared to this strong base. And that's why all these curves back here that we looked at the other day, they kind of look all the same after the equivalence point. They all mesh into one curve at the end because the pH is dictated by that excess sodium hydroxide. Okay, so we're going to take a quick look, or you should not take a quick look, but study the next few plates and see how these different parts require different logic and different calculations to find the pH. Okay, so now we're going to do these parts with an example, and you should study this. I'm just going to go over it because the answers are all here. So here's some back tests that I gave in 2004, and this is when, you know, students came to class and they were all problem and written, and so you'd have to figure it out, and then I would grade your problem. But now it's all online, so it's a little different. Instead of looking at back tests to study for your exams, you should be looking at homework because that's where I modeled your exam from, as the homeworks. But anyway, it says 50 milliliters of this concentration of benzoic acid, which is abbreviated HBZ, so it's monoprotic, is titrated with the strong base. Calculate the pH at these following points in the titration curve, and that's the ones associated with the ones we just were talking about before anything's titrated, 0 mils, and then somewhere in that buffer region, then I assume this is at equivalence point, and we'll see that, and then this one is after equivalence point. So A corresponds to 0 mils titrated. So what's that going to look like? Well, geez, it's just the weak base benzoic acid in water. And you know how to do those kind of ice tables. So it dissociates into its ions and comes to equilibrium. So you start off with the initial concentration, 0, 0, and fill out the ice table. Neglect X, check the 5% rule, calculate X, and X is associated with H plus. So minus the log of X is the pH. And so when you go back and study these plates, hide the answers and work through each one of those points. All right, so this one was more or less a review of something you already know how to do. Now the buffer region one is B. Now for this approach here, you're adding in some sodium hydroxide. So we know how to handle these type of problems because we looked at what to do with buffers, right? So the first thing you have to consider is number one, the complete neutralization limiting reagent problem, Chem 200 problem that takes place between a strong base and a weak acid. So number one, the complete reaction, neutralization to create salty water, but it's not an equivalent amount. And so how do we know? We can take the concentration of the weak base, multiply it by its volume, so we know how many moles of weak base are in that flask that's getting titrated. We know the concentration of the NaOH in the burette, and we know that we want to find the pH at 10 milliliters. Okay, so I know the moles of OH minus that's introduced at that point in the titration. I also know that these guys are going to react until the limiting reagent runs out, which is the hydroxide. And I could subtract the two and find out how much weak acid I have left. But I also have to remember that when this reacted up here, this was the limiting reagent and it produced salty water. And in that salty water, I have Na plus, a spectator, I don't care, but I have the conjugate base, Bz minus. So now this ice table setup looks like a buffer problem where I have a weak acid in the presence of its conjugate base. And that's why that part of the curve is often referred to as the buffer region. So I just take the moles, divide it by the total volume. I have to add up the two volumes that were introduced. So it's 60 mils. I take these moles, divide it by 0.06 liters, and I get these new concentrations for initial of the weak acid that's left over, the conjugate base that's created. And now I could use those in the Henderson-Hasselbalch equation to calculate the pH, or I could just put them in here in the ice table and neglect this X. Check the 5% rule, which you don't usually do when you use the Henderson-Hasselbalch, so that's the danger. But like someone asked yesterday, almost always, we give problems so you don't have to solve the quadratic. So, yeah, whatever. Anyway, you can find X from that. X is related to the pH because it equals the H plus concentration. So minus the log of X gives you your pH. And that's anywhere before equivalence point when you have an excess of weak acid. You're going to set it up like this. Any questions so far? All righty. Now on to the equivalence point. So like when you go back and study these, hide the answers and you try to create this, think through the logic of what's happening and what you need to consider. Okay. Now, this is the second the third of the numbers in a possible titration curve problem. Now, the third corresponds to the equivalence point. How do I know? Well, they tell me to calculate the pH when 25 milliliters of NaOH was added into that benzoic acid. So again, I know the moles of benzoic acid initially from that molarity times volume. I know the moles of NaOH that was introduced at this point when you added 25 milliliters. And I see, wow, they're the same. So again, this is a complete reaction. The limiting reagent in this case turns out to be both reactants. They're both gone. There's no weak acid left, but as much of the acid and base that reacted created that much conjugate base. And you know that from your Chem 200 limiting reagent problems. So now I just need to take that moles, realize that it's the moles of Bz minus. I add up the volumes to get the total volume. I divide that moles by the total volume, and I get the initial concentration of the conjugate base. Now you see that the ice table looks a little different than it did before in the buffer region because you're not starting out with any weak acid anymore. It's all gone. Now you have all conjugate base. But no big deal. You've done weak base equilibrium before. So you set up the ice table. Initially, these are 0. You let them come to equilibrium and you find out how much. This is where you're going to have to be careful about the value you use for the equilibrium constant, realizing this equilibrium constant is not the same as the previous one, but it's related to it through Kw. We know the equilibrium constant relationship, Ka times Kb of conjugates equal Kw. All right, so we can calculate that Kb over here using the Ka and know that that's equal to x squared, x times x squared, divided by the concentration of the reactant, which is the conjugate base. Check the 5% rule, calculate x, but be careful. This x is no longer directly related to the pH. It's related to the POH because it equals the hydroxide concentration. So I can use that x to calculate the POH and then subtract that from 14 to find the pH. So there's a lot of stuff to remember in there. Again, when you study this at equivalence point, you're going to want to hide everything and work through that logic. All right, the last point is after equivalence. And I know it's after equivalence because at 30 mils, I see that the strong base gives me more moles than the weak acid that was there. Again, it's a Chem 200 problem to make salty water. In the water, I have that many moles of the conjugate base, but I can ignore it because what little hydroxides generated from that is negligible compared to the excess hydroxide that was added into the flask at that point in the titration. So again, all I need to know is the excess hydroxide, that is the hydroxide number of moles. I divide that by the total volume, which is a sum of the acid and the sum of the base. I get its concentration right here. And then I use that to find the POH. And then I subtract it from 14 to find the pH. And that's pretty much as hard as it gets for the titration problems. That covers all the points on a titration curve that you could have to deal with. Any questions on that? Okay, then I'm just going to state one more thing before we move on. You should probably go through this, and you'll probably have some homework problems, and you can look up problems in the book as well, but go through it. But this time, instead of using a weak acid, use a weak base with a strong acid in the burette. Now, how's that going to change things? Well, this is going to start out very high because the pH is going to be high because you're titrating into a weak base. Again, you're going to have a buffer region where you have the leftover weak base in the generated acid up here. You're going to need a Kb initially to solve this ice table. And then at the equivalence point, all your base is going to be wiped out, and the only thing you're going to have is your conjugate acid. So the pH at equivalence point is going to be lower than 7. And then after the equivalence point, the pH is going to be dictated by the excess strong acid, like hydrochloric. But it's kind of the same, but completely different, if you know what I mean. So you could think through that problem on your own, and you'll probably see one in the homework, and you should know from analogy with this how it's different and what to do. So initially here you'd have a Kb, and then at equivalence point you would take the Kb and calculate the Ka, because that's what you're going to need at equivalence when you have salty water. But in that case, it's going to have the conjugate acid. I hope that sounds reasonable. But you should study that. Any questions? All right. Now we're going to go on to a different topic, but of course it's related. We're going to introduce another equilibrium constant for solids. So this plate says, consider when you have two ions, lead and iodide, and this is wrong. I just noticed that 2 shouldn't be there. It should be over here. So sorry about that typo. Very weird. Anyway, you know this is an insoluble salt from your solubility rules from Chem 200. You put lead in the presence, and this should be a 2 up here. You put lead in the presence of iodide, and you form lead iodide, this insoluble yellow precipitate. You may recall from lab if you had it. So we want to kind of understand this as far as what concentrations we need to have precipitates. And when this dissolves, say in pure water, and comes to equilibrium with those ions, what are those concentrations? So this is right up the alley for an ice table type of approach for solids. So we define the Ksp, the solubility product constant, and it's very similar to equilibrium constants that we've looked at already. Now notice that these equilibriums for solids, these Ksps, have the solid on the left of the equilibrium always, and then the ions are on the right. So barium sulfate is another insoluble type solid, but it comes to equilibrium with its ions in water. And so we can write this. We can define the equilibrium constant using the law of mass action. Note that that's a solid, that it's incorporated into that equilibrium constant. And when it is, it's called the Ksp, the solubility product constant. So for this example, it equals the barium 2+ ion times the concentration of the sulfate ion at equilibrium. All right. So there's no difference, or very little difference, from the equilibriums that we've dealt with so far. Now it's just a solid. Now, why do they call it the solubility product constant? No one ever really says why, but I think it's related to the definition of the Ksp in terms of solubility. So what is solubility? Solubility is just the amount of that solid that dissolves in a given amount of solution. And so that amount can be either measured in moles, and in that case, you would call it molarity, the amount per volume, or it could be measured in some other units like grams per liter. And you can convert from one to the other. So that's what solubility is, how much of that solid dissolves into solution. And of course, this equilibrium constant, like all other equilibrium constants, are temperature dependent. So the ones you have in your textbook will always be at room temperature. And usually it says on the table what temperature the equilibrium constants refer to. So you can convert from the solubility in these units to these units, and then there's the relationship between the solubility and Ksp, just like you related the pH to the Ksp, or the percent ionization to the Ksp. Now you're going to relate the solubility of a insoluble solid to the Ksp. So how is it related? Here's an example. I have silver chloride solid in equilibrium with its ions. So I can set up the ice table. In this case, they told me what the solubility. It has a solubility of this amount. What is the Ksp? So I'm going to have to relate the solubility. So we see the familiar ice table here. And I noticed that X is the concentration of He+. It's also the concentration of Cl- at equilibrium. And it also tells me how much AgCl is dissolved in that volume of solution. So in our old ice table, this X, this is the solubility in units of moles per liter. So sometimes in the book, you'll see them change this X value to an S when you're dealing with a solid, right? So we set it up just like before. We don't have to worry about this concentration. It's already taken care of in the Ksp. We see that the Ksp is defined as the concentration of the products to their stoichiometric coefficients at equilibrium. So it equals X squared, but X is the solubility. So it's the product of the ion solubility, or I should say the solid solubilities. It's the ion concentrations. So that's probably why they call it the solubility product constant, because for simple cases without stoichiometric coefficients, it's just the simple product of the solubilities. Any questions on that? So either everybody left or everybody understands this. I'll pretend it's the latter.
It makes sense until we go to do our homework.
That always happens, man.
Agreed.
That's like Murphy's Law or something. Actually, yeah, we'll get to this in thermodynamics. All right. So far so good. It's not too much different than what you've dealt with so far, but now instead of pH, you know how you had to relate X to pH, it's minus the log of X because X equals H plus concentration. Now X or S, whatever you want to put there as your algebraic parameter, that is the solubility in units of moles per liter. So when I calculate that X, I find this value. I can use the molar mass to convert moles to grams and calculate it in these units if I want. Okay, so who cares? That's just another way of saying the solubility in different units. But all this other stuff is the same. It's the same song and dance. We're just relating solubility to the KSP, whereas before we were relating things like a POH or the pH or the percent ionization. All right, so things you have to worry about now or watch out for dealing with KSPs in solids. One is stoichiometric coefficients are going to be more prevalent than they were in the acid bases because oftentimes with our acids and bases, it was a one-to-one type of relationship. But in solids, you can get examples where it's not, and this is one. So where does that come into play when solving your ice table to calculate the solubility? All right, so when we do the ice table, we see for every one of these guys that breaks up, one of these form. So X is, in fact, the solubility of the solid in units of moles per liter. Okay, so the stoichiometric coefficient here comes into play. I get 2 times the solubility of the nitride ion at equilibrium. But so what? All right, I know how to deal with that. I know the stoichiometric coefficient comes into play here. But now look, when you define that equilibrium constant, it also comes into play right here. So you can't forget that too as well. So the KSP equals X times the quantity 2X squared, because 2X is the equilibrium concentration of the nitride, and I have to square that according to the definition of the equilibrium constant using the law of mass action, which says the concentrations of the products to their stoichiometric coefficients divided by the reactant. But in this case, the reactant's a solid, so that's not shown here. It's already taken care of in that equilibrium constant. So I see now that the equilibrium constant is kind of a funky product of solubility. It's 4 times the solubility cubed in this case because it has a stoichiometric coefficient of 2 here. But how? I can solve that, that mathematical equation. I just take the KSP, which you can look up in your textbook, or if you're lucky enough, they'll give it to you in the problem. I equate it there. I divide it by 4. I take the cube root, and I have my solubility. And I can convert it to other units if I want. Any questions on that? Okay. This is something we already mentioned. You can go back and read that on your own. And this plate introduces another interesting concept about the solubility product constant, or the KSP. Now, the KSPs, you can look up for a bunch of insoluble salts, and they're in your textbook. And you can look up tables of KSPs online. And what they tell you is not only all the ordinary stuff that we know about acids and bases equilibriums, but they also give you maximum ion concentrations that are allowed in solution. And that kind of falls out with the Q concept. In other words, if I look at some equilibrium of a insoluble salt like this one, then I can define my Ksp right away for that insoluble salt. And I've done that there. It's mercury times chloride squared. And I can look up the value for that. So what this is telling me is that this concentration of mercury times the concentration of chloride squared at equilibrium has to equal this value. If it doesn't equal that value, then it's not at equilibrium, right? And I could calculate a Q for any other situation. Q is going to equal the same definition of K as before, but it doesn't have to have equilibrium concentrations. But the Q concept is still true. In other words, if Q is greater than K, does anybody know what's going to happen? Okay, I'll take that as a no.
Like no reaction would actually happen.
Well, if Q is greater than K, that means this concentration times this concentration in solution squared is greater than the equilibrium constant. So that tells us, if you look back in your notes, that the reaction must shift to the left,
Okay, yeah.
right? And you would predict more solid or a precipitation to occur. And you can also play the game where Q is less than K. If Q is less than K, then there's not enough product. So you would say shifts right and the solid dissolves. Right, so that's the old Q concept, and it's still at play here. And all the Chatelier's principle stuff is at play as well, and we'll look at that a little bit. But it also tells you kind of like the speed limit or the maximum ion concentration that you can have without a precipitation, right? Say Q is less than K and there's no solid to be dissolved, then you're shit out of luck. Nothing's going to happen, right? It's not going to precipitate. And so we can think of another situation where one of the ions has a certain concentration from another source. In this solution, there happens to be 0.01 molar of this mercury ion. So this guy's already set. Then the question you can ask is, what concentration does Cl minus have to be before precipitation takes place? Then I can use my constant, Ksp, and I can solve for this unknown concentration and show what value that concentration would need to be built up to before I had a precipitation. Okay, so you can kind of ask interesting questions. And this kind of comes in handy because say you want to fluorinate your water because of health reasons. I don't know, it's good for your teeth at certain concentrations. But you know that fluorine or fluoride, F minus, makes an insoluble salt with calcium, and calcium's also in the water. So you find out what the concentration of calcium is in that water, and then you can calculate the fluoride concentration that you can add up to without a solid, because you don't want to be drinking solids in your water. So it has practical applications. The speed limit, this Ksp acts as the maximum amount of ion concentration that you can have before precipitation takes place. So we're going to deal with those type of problems. And we're going to look at Le Chatelier's principles in terms of the common ion effect, changes in pH, and the presence of complexing agents on the solubility of these insoluble salts. Now, I think you can probably figure this out. For number one, the common ion effect. Say I have that calcium fluoride that I was just talking about. You know, you're fluorinating water, there's calcium in the water, you don't want a precipitation or whatever. So this just happens to be the next equilibrium. And I have this calcium fluoride in equilibrium with its ions. And it says here, I'm going to add in some NaF to this. What's going to happen according to the Chatelier's principle? This is at equilibrium, this reaction here, and I add in some sodium fluoride. What happens?
It shifts to the left
Why?
because you're adding more of the reactants
No, that's a product. You're right.
product.
Yeah, because you're right. Na plus F minus. This is a spectator. This I recognize as an ion that's common to this equilibrium. So Le Chatelier's principle says, oh my, there's too much. The stress is there's too much F minus, too much product. So you said shifts left. And shifting left is going to cause calcium fluoride to form, not break up, form. So what do you think happens to the solubility of calcium fluoride in the presence of a common ion? Do you think it's more soluble or less soluble? If more,
Solubility decreases.
yeah, exactly, because more calcium fluoride is being formed. So the solubility, in effect, goes down. It decreases. So there you go. You have your first Le Chatelier's principle effect on the solubility. Okay. All right. Now, you added some fluoride to shift to the left. What if I add an acid into the equilibrium? Can you see anything that might happen here? In other words, if I make the pH go down, add an acid. Will it react with anything in this equilibrium? Five, four,
Would
three,
it
two,
react
one.
with the F minus?
Yes. Why? Why would it?
Because that can accept a proton.
Yeah, because F minus is a,
Base.
Base.
yeah, it's a base. So if I add an acid, this is gonna form an equilibrium. It's gonna form some HF, and the concentration of F minus is gonna decrease. Le Chatelier's principle says, oh, the stress is not enough F minus. Which way does the reaction shift?
To the right.
To the right. And what happens to the solubility in that case?
Increase.
It increases. Yeah, so that's pretty easy. So you have number 1 and 2, and we're going to get to 3 in a little bit, but I just want to go over the next few slides to show you what you already know. So I have the solubility of that calcium fluoride in the presence of a common ion, and I see the solubility decreases drastically as the concentration of that common ion increases. Solubility goes down. And how can you calculate that using an ice table? Well, here's the solubility of silver chloride in pure water. Here's the usual ice table here. We solve for X, that's the solubility, using the Ksp of silver chloride. But now the question is, how's that solubility change in the presence of a common ion? You already know it goes down. How far? You can calculate, quantify the amount. All right, it's going to be in 0.02 molar aluminum chloride. That gives rise to 3 chlorides per 1 mole, so it's 0.06 molar chloride. That changes our ice table now to look like this, where we have initially another source of chloride. This X is still the solubility, and we can calculate it, and we see that now it's much smaller in the presence of a common ion than it was in pure water, just like you thought. Okay. We talked about how pH can affect the solubility. Here we have an insoluble salt. You can imagine the ice table. And now we're going to have something going on here with this hydroxide. Magnesium hydroxide, that's kind of like the white powdery stuff, magnesium and calcium hydroxide that you find in the sink, in the bathtub. It forms solids from your water. One way to clean that up is add a source of an acid like a citrus acid, like lemon juice.
Vinegar.
Or vinegar, thank you. Yeah, some acid, lemon juice, vinegar. That's going to react with the hydroxide in the solid, shift the reaction to the right, and the solubility is going to increase. It's going to dissolve and it's going to clean up your sink. If you have misters, they get stuck with the same thing. The little hole gets stuck with this solid. You just let them sit in some lemon juice. You put them back into your garden area or the windshield wipers on your car. It has that little hole that shoots up the cleaning solution, and it cleans it out. You put it back in, and it's perfect. So this shows you how the solubility of some insoluble salt that is in equilibrium with its ions, and one of the ions is an acid or a base. In this case, it's a base. So as the pH goes down, you're adding more acid and the solubility blows up, just like you said it would. All right, that leaves us the last one, which is the complexing agents. And we sort of talked about metal complexes. So again, we look at the solubility of silver chloride like we did before. We calculated that solubility. It was 1.35 times 10 to the fifth, back there somewhere. If you add ammonia into this equilibrium of this solid with its ions, so it's an equilibrium with Ag plus Cl minus, the solubility greatly increases. Why? It's because you're forming a complex with one of the ions that are in equilibrium, essentially taking it out of the equilibrium. The stress is not enough silver. So according to Le Chatelier's principle, it shifts to the right and dissolves. Okay. And this is the reaction that takes place between metal ions and what they call ligands. And at the end of this course, we're going to look at these complexes in some detail and see what they're made up of, how we envision they're being made. But it's good enough to just to write this for now, saying that some metals form complexes with non-metal groups, usually something with a lone pair of electrons like a nitrogen. Oxygens have lone pairs of electrons like water, and so forth. And they form these complexes that are ions, and therefore they're dissolved in solution. Now notice the reaction of a complex has the complex on the right forming, and the ions or the other stuff's on the left. Whereas for Ksp, the solid is on the left and the ions are on the right. Okay. But there's the usual definition using the law of mass action for this equilibrium constant. It's called the Kf. And that refers to the formation of a complex ion. And this is what's known as the complex ion. So we can form it in the usual way, the concentration of the products to their stoichiometric coefficients over the concentration of the reactants to their stoichiometric coefficients. And we have these values. Notice the values, unlike all the other equilibrium constants that we've looked at so far, these guys are big. So we would say that these equilibrium lie to the right towards the formation of the complex ion. And we can use this knowledge to calculate the new solubility of insoluble salts that form complexes with these non-metal ligands, they're called. And all of these complexes, like I said, are on the right of the equilibrium, so they're all over here. The ions are on the left, and the Kfs are all very enormous. So there's a strong force for making these complexes. And when we look at these again at the end of the term, we'll go back and we'll talk about reasons why they should be large. But very quickly, I want to introduce a possible problem, which is what is the new solubility in the presence of ammonia, which I alluded to back here, but I didn't give an example. So we know from a previous calculation that for silver chloride, the solubility we found was 1.35 times 10 to the minus fifth molar in pure water. So the question is that I'm going to pose now is what's the new solubility? What's S in, I don't know, let's say 3.5 molar NH3. Now, how would I think about solving a problem like that? Well, the first thing I would note is that silver chloride forms this equilibrium with its ions. And I know that the formation of the complex ion is going to form this way. NH3, 2, and this whole thing is charged +1. I know this Ksp for this reaction equals 1.82 times 10 to the minus 10th because I looked it up. And I know the Kf for this is 1.7 times 10 to the 7. So I can add these up, cross this out with this, and I get silver chloride solid plus 2 ammonias give me Ag, Ag NH3 2 plus, there's no chloride there, plus Cl minus. And I know what the new constant is here. Does anybody know how I find the constant for that reaction? Okay, you have to review some of the things that we talked about. When you add up two reactions to get a third,
You multiply.
yeah, you multiply them. So the K for this is that multiply Ksp times Kf. Okay, so now if I'm in 3 molar, how does that change my ice table? This is a solid. I got 3.5 molar. This is 0, 0, minus the 2s, 2 times solubility. S, 3.5 minus 2s. So the Ksp, which is 3.09 times 10 to the minus 3, has to equal S squared over 3.5 minus 2s. And this whole thing's got to be squared, right? Because of that stoichiometric coefficient comes into play here and in the definition of the equilibrium constant. So I can take the square root of both sides to get rid of those squares. And when I do that, I get 0.0556 equals S over 3.5 minus 2s. And then I can bring the 3.5 minus 2s over to this side and multiply it out. So I'd get 0.195 minus 0.111 s. That equals S. Or 0.195 equals 1.11 s, or S equals 0.176 molar. So you see the solubility increased drastically from when it's in pure water versus when it's in 3.5 molar ammonia. Okay, so you might see a problem like that. Just in case you do, I wanted you to have some method of solving it. Then this next plate talks about amphoteric oxides, which are kind of cool. They can act as acids or bases, but I don't think we'll be dealing with it too much. Here's one reason why they're cool. Say you have some solution, aluminum 3+, and you add hydroxide to it, it forms this complex. Notice that the charge goes down for every oxide or hydroxide, I should say, that the aluminum takes on and displaces the water. So it can take on another one, charge goes down, takes on another one. Now there's no charge in a solid, falls out of solution. Then you can take that solid, you can keep adding hydroxide, get another one, and now it's dissolved. So it's kind of cool. You can keep adding the same thing, get a precipitate, keep adding the same thing, and then it dissolves. And this is why. As far as problems or anything, you won't have anything dealing with that. Remember, the Q concept is at play with these insoluble salts, and we talked about, which way things are going to take place as far as calculating a Q, comparing it to K, and then coming to one of these three possible conclusions. This whole idea implies something, though, that with the knowledge of different solubility product constants and their values, we could envision maybe of selectively removing ions from a mixture of ions based on their solubility product constant values. So what does that mean? I want to look at that real quick. Say you have a solution and it contains zinc and copper. You know that both of these ions, zinc and copper, form an insoluble salt with sulfide. Furthermore, you know they're KSPs because you looked them up. If I have a solution of these metals and I take an eyedropper and I start adding sulfide into it, well, you tell me, which one do you think is going to precipitate first, the copper sulfide or the zinc sulfide?
The zinc sulfide.
Okay. That was, you had a 50-50 chance there just to guess, and you guessed wrong, but it's okay. I don't expect you to know this just yet. We just introduced it, and it's going to take some time to get used to the things that are happening here. Now, remember, these KSPs are defined in terms of the concentrations of the ions that they're in equilibrium with. So this is defined as copper 2+ times sulfide. And this guy over here is defined as the zinc 2+ and sulfide concentration. Look at the values. This is much smaller than this. So that tells me that I have to have smaller concentrations of these ions in solution compared to these guys. So if I have a solution of the same concentration of metals, I know that I'll need a lot less sulfide for this precipitate of the copper because its KSP, which indicates the maximum amount of dissolved ions allowed, is going to be lower than in this case. So if I did drop her out, I drop, the concentration of sulfide is going to increase up, up, up until I get to a threshold here. And then the copper is going to precipitate. And then this concentration is going to go down until the zinc starts to precipitate at some threshold. And these thresholds we can calculate using the equilibrium constants. So I know that's kind of cloudy right now, but let's look at an example. Here's an example problem of using selective precipitation. The problem starts off by saying, all right, let's consider a solution where we have the same concentration of two different metal ions, silver and lead, and they're 0.02 molar. I can look up the KSPs of each one of those guys, right? And I know what those equal. Like the KSP of the silver chromate equals the concentration of silver times the concentration of chromate. What am I missing? If you don't know what I'm missing, then you need to do the ice table. I'm missing a stoichiometric coefficient that goes up here over the silver. So that's defined, and I know its value because it told me 9.0 times 10 to the minus 12th. And I know the same thing for the KSP of the other guy, lead chromate. That's going to be simpler. It's just the concentration of lead, 2 plus, times the concentration of chromate. And that, they told me, was 1.8 times 10 to the minus 14. Now, let me ask you, in the same situation, I take a dropper, and this time it has chromate in it, CrO4 minus, and I'm going to drop, 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 drop. Which one is going to precipitate first?
Does the silver actually double because of the coefficient?
Well, yeah, we can,
Like double ions?
we can figure that out exactly, what the concentration of chromate we need in each situation. But if you're going to guess, which one would you guess would precipitate first and why? Just a straight shot in the dark.
Well, lead,
Why?
because it's smaller.
Absolutely. Now,
But not if the silver is actually doubled.
yes, okay, we're going to square it, but we can calculate this exactly, this amount of chromate, because we know in this case, this is 0.02 molar, and this is 0.02 molar. So the amount of chromate we can solve for in each case and see how much we need.
Okay, yeah.
So chromate 2 minus needed for precipitation. So I'll say needed here. Needed for precipitation equals, if you do that math, you should get 2.3 times 10 to the minus 8 molar. And in this case, the amount of chromate needed for precipitation, I calculated to be 9.0 times 10 to the minus 13 molar. So you're right. The lead is going to precipitate first because as you dropper load it in, the concentration of chromate increases from 0 to 9 times 10 to the minus 13, and then lead starts to precipitate out.
Okay.
Okay. So good, we calculated exactly. The question that's really interesting after this, that you'll see maybe on problems, is what is the lead concentration? What is the lead concentration at the point when the silver starts to precipitate out? Now, that's an interesting question. And that'll tell me, is this really a selective precipitation? Can I get pretty much all of the lead out before the silver starts to precipitate? How much lead is left at that point? And it's really simple to solve for these type problems. So I just wanted to show you this. Okay, I know what the Ksp for the lead is. Ksp for the lead chromate, remember, that equals 1.8 times 10 to the minus 14. And I know that that equals the concentration of lead times the concentration of chromate. And I know I need this amount for silver to start to precipitate. I also know that as I dropper load the chromate in, it reaches this concentration, then lead starts to precipitate out. So lead concentration is going to go down from 0.02 molar. The question is, what is it going to be when the chromate precipitates out with the silver? So I need this to be 2.3 times 10 to the minus 8. And that'll answer my question. So I go ahead, plug it in, and I calculate the concentration of lead that's left that started at 0.02 molar. And now I find that it has to be 7.8 times 10 to the minus 7 molar. That's just a trace amount. That's almost undetectable by our modern day tools. So it is pretty selective. Your first precipitate is almost solely the lead, and then your second precipitate is going to be due to the silver chromate. Any questions on that? And so again, this kind of explains the stuff that we just talked about. Then the last thing is just a prelude to stuff that we might deal with at the end of the course, which is quantitative versus qualitative analysis. You don't have to know this for the exam. It's just tacked on here because it just goes with all the ideas that we talked about with the KSP. You can have a quantitative analysis, how much of each one. So you'd have to precipitate it out and weigh it. Qualitative is you use the KSPs to identify ions in an unknown. And so based off of these KSPs, they've made up procedures for taking unknowns of a large number of ions. Like all this, okay, here's my possible unknown. I can have all these. How can I find each one of those? Well, I add in a source of chloride and precipitate all the ions up here that form chloride insolubles. I centrifuge, I decant, and I analyze both the supernatant and the solids. I try to break those solids up using maybe my knowledge of how silver, in this case, will react with ammonia, because I know the Kf forms this complex, and I can dissolve that and centrifuge decant the other two and separate, and keep doing this kind of thing and identify all the ions in my unknown. So you're not going to have to do that, but this kind of indicates what you can use KSPs for.
I think we did that in 152. It was pretty extensive.
Oh, okay. Well,
It was fun too.
but did you know that you were just following the procedures, but you didn't know those procedures were built off the knowledge of the equilibrium constants?
Nope.
Yeah, see, now you know. And now you know how to maybe tweak those procedures and make them fit to whatever problem you're trying to solve.
That's kind of cool.
Yeah, I think so. I agree. And as they say, beep, 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 but eep. That's all, folks.
Thank you.
Yeah, anybody have any questions, just let me know. And by the way, that was from an old cartoon when I was a kid. I don't know if you know that reference at all.
Thanks, Professor.
You
Thank you,
got it.
Professor.
You got it,
A
guys.
good
Thank
break.
you.
Thanks.
Yeah, you too.